We're going to discuss a little bit about knots and links and about how to use coloring knots and links to study them. I'll take, say, a piece of string and I'll project it on a blackboard or a piece of paper. That's called a projection of a knot. And you see when I project it, there are overs and unders that tell me how it looked when it was back in three-dimensional space. Now, of course, you could think of a piece of string as just going like a line, but in mathematics, it's convenient to take the two ends of the string and connect them together so that it forms a circle all the way around, right? If you don't stick the two ends together, you can, of course, always unknot something just by pulling the strand through. And I'm trying to avoid doing that so that I can talk about when two knots are different. It looks like a circle in the sense that if I had a little ant sitting on this, for example, here's my little ant, he would walk around this way and then they keep going and keep going and keep going. And then he would come back gradually, he or she, actually it's she in case of ants, would come back to where she was at the very beginning. And that's what makes it a circle. But it's a complicated circle in that it's not just like this, right? This would be what we call the trivial knot or the unknot, which has no knottings. This is a knot in the sense that you can't get from this picture to this picture without doing something discontinuous, like cutting the knot or something like that. In mathematics, we're interested in studying classification of knots. What can you say about knots? How many are there with a certain level of knottings and things like that? How do you actually prove that these two knots are different? It's not so obvious. In other words, you notice that when you're a kid, for example, I loved to do it when I was a kid, you like taking some piece of string, making it look like it's really complicatedly knotted, and then you fool the adults by showing that it just yanks out, right? So how do you know that isn't true of this, or that you couldn't get from this to this by doing something like making it much more complicated and then somehow yanking it out? In fact, we can prove that there's no way to go from this to this. The unknot and this knot is called the trefoil knot. It's the first non-trivial knot. And how do you prove that there's no way to go from this to this, right? How do you know that if you did a zillion ways of moving it around, the knottings wouldn't cancel out, right?
So just making it is not enough and like fiddling around with it.
That's right. You could say, why don't you just count the number of crossings, right? The trouble is you can change the number of crossings in various ways in a knot. So this knot has 3 crossings where there's an over going on top of an under. There's one over here, there's another one over here, and there's another one over here. So there are 3 places where one strand lies on top of another, like that. So you could say, why don't you just count the number of crossings? This one has 0 crossings, this one has 3 crossings. And it is true that the minimum number of crossings you need for this one is 3. And for this one, the number of crossings is 0. But the trouble is that you can change the crossing numbers. For example, a simple dumb bunny way to change the crossing numbers is introduce into a piece of the knot a pigtail like that, which obviously you could yank out, right? There are 3 basic ways that you can introduce more crossings in a knot. Those are called the Reidemeister moves. This is the first one, the simplest one. And there are 2 more that involve more strands. And the problem is that the Reidemeister moves seem to increase the number of crossings, but you can do the opposite and decrease. And so you haven't solved the problem of why can't you get rid of all the crossings by doing a lot of these Reidemeister moves, maybe first complicated and make 1,000,000 crossings, but then yank it out and get down to 0. See what I mean?
Is that just like a cosmetic crossing, or is it like a lifetime crossing?
Absolutely, that's the issue. Now let me draw for you the other Reidemeister moves, and any motion of a knot can be broken up into a series of these simple motions. So this is one, the pigtail, which you could yank out. You could yank the pigtail out to just get a straight line, for example, in a segment of the knot. Or you could have 2 segments of the knot that are, for example, not doing anything at all, lying next to each other, and then you pull one strand over the other one. So you would take this and you could move it so that it would look, for example, like this, with one strand going over and the other one just going always under. And obviously you could yank this back to look like that, right? Or vice versa. So that's the Reidemeister 2. And there's one more complicated motion, R3, which involves 3 strands. And there, what you do is you have 2 strands, one is crossing over the other, and a third strand comes in and then goes, let's say, over both of them, say, like that. So this looks like this. And then what I could do when I have 3 strands, for example, I could move it to a picture where this guy that's going always over moves over further up. Instead of down here, he could move over here over all of them like that. Get what I mean? And now, obviously, I could do that by just pulling the third strand higher. So that's R3. So those are obvious simple moves that you can do and change the projection of a knot. And now the question is, how do you prove that there's no way to go from the trefoil knot to the unknot using these simple moves? Or to give another example, there's a simple knot called a figure eight, and you see it's going to have in the middle something that looks like a figure eight, roughly. This one has 0 crossings. This one has 3 crossings. This one, let's count them, has 1, 2, 3, 4 crossings. This is a 4-crossing knot, and one can prove that actually not only is there no way to go from this one to the unknot, but also these are 2 different knots. In other words, just by moving this around without cutting it, there's no way to go from the trefoil to the figure eight or the figure eight to the trefoil. So here we have an example already right away of 3 really different knots. We can complicate them by doing these motions, Reidemeister moves. We might try to simplify them by other Reidemeister moves. But in fact, no matter how many zillions of moves we make, these 3 are all different, and there's no way to go from one to the other.
So, Professor, it feels like these Reidemeister moves, they're like cosmetic moves. They're like...
That's right. They don't change the underlying type of the knot. They change the way it sits in 3-dimensional space, but they're equivalent to each other as knots in the sense that one can be deformed continuously to the other without cutting it. There are tables of knots which tabulate knots by the minimum number of crossings. So this is the only knot with 0 crossings. This is the first non-trivial knot. The one that's not the unknot is the trefoil knot with 3 crossings. This is the one with 4 crossings. There are 2 with 5 crossings. And then the number of knots begins to go up very fast. By the time you're up into, say, 12 crossing knots, you've got tens of thousands of them and so on. The question is, how do you prove that they're different from each other? Now, mathematicians have a whole bunch of different methods of doing that, using geometry, using algebra, using a bunch of different ideas. But there's a very pretty old idea that can be explained to bright high school students by using coloring of knots. And that's what I propose to show you because it's very visual and you can just see it. So the idea is the following. I'm going to consider the following problem, and for simplicity, I'm just going to be working with 3 colors. So what do I mean by 3 coloring? I mean that when I take a projection of a knot, like this picture over here, I'm going to color each of the apparent segments that I see under the projection. So for example, in this case, because I had 4 crossings, they look like there are 4 segments over here where it's unbroken. There's one here, and there's another one that goes all the way around here, and another one here, and so on. The 4 crossings gave me 4 segments that it's broken up into, and I'm going to try to color the knot using 3 different colors. And what I'm going to do is I'm going to try coloring it in a way so that with a certain rules about how I'm allowed to color it, and then I'll see that with these rules, some knots can be 3-colored and some knots cannot be 3-colored, and that's going to let me distinguish one kind of knot from another kind of knot. So I'll be dividing the knots into 2 kinds, those which can be 3-colored and those which cannot be 3-colored. Now, that's not a way of telling all knots apart, because it's kind of crude that I'm only dividing them up into 2 sets. But still, it'll tell me that some of them are not equal, cannot be deformed to the other ones. Now, I have to have a rule, because if I have no rule, anything could be colored with 3 colors, and then I'm not gaining any information. So I have to have a rule. But I want to have a rule that's compatible with my Reidemeister moves, in the sense that if I could color a knot before, there's an obvious way to then color it after I do one of these Reidemeister moves. So when I get to a crossing, there's an over one, and then there are 2 unders, one coming in, the other side, another one. At a crossing, I will see 3 colors because I will have the color of the over and then the 2 unders coming there. So I have to have 3 different colors here, and I have to have some rule limiting what happens at a crossing. One obvious rule to try to use is say, well, since I'm trying to do this with 3 colors, and at a crossing there are 3 strands coming together, the 2 unders and the over, maybe the rule should just be at a crossing point like this, you get all 3 different colors. That seems like the obvious rule to try. Insist that at a crossing it looks something like blue over here, red over here, and say green. And I do those 3 colors together, and that would be the rule to have. That's a natural first guess. It almost works, but not quite, The reason it doesn't quite work, you can see already, because it has to be compatible with these Reidemeister moves, so that as I do the Reidemeister moves, the coloration or the colorability is maintained as I do them. Now, if I do, for example, even just a pigtail, so I start off with a single strand like that, and then I take this strand, so this is somewhere in a big knot diagram, somewhere in it, and I take this pigtail, and that, of course, I can yank out and go back to what I had before, so I can go back and forth between these two. But notice what happens, that at the crossing, I'm coming in from somewhere other stuff in the knot, so I'm coming in blue, and I'm going out blue. Well, that's it. Then I've got to be blue all the way. So you can see that at this crossing that I've introduced with the pigtail, in order to make it compatible with what I had before, I have no choice but to allow at a crossing all three colors to be the same at that crossing. So I'm going to modify my first guess for the possibility that all three are the same. Our tentative new rule is going to be all three different or all three the same. Okay? And that's a rule which we can check now, case by case, is compatible with these Reidemeister moves. And now I do the second Reidemeister move, and the second Reidemeister move consisted of pulling one of these over the other. I'm coming in from elsewhere in the knot, so I can't change the ends of this. So now I'm going to have one of this is coming in blue, the other one is still coming in red also. And in fact, they've got to go out the same way to fit with what's going on elsewhere in the knot. So here, this is going to go out red, and this is still going to go out blue like it did before over here. But what happens in between? Well, in between, this red guy goes over here and comes over in this Reidemeister move here, and then goes back here and connects up here. Fine. This one is going to continue all the way down, and then, of course, that's something I could yank out by the second Reidemeister move, just by pulling this back over there, and then I would get my original picture. But see what happens. Remember, my rule was that at a crossing, all three are different or all three are the same. So at this crossing, I have here blue and red, so now I've got to get green coming out of there. I have green coming out of there, coming down here, and here's green. And now I'm in luck, because there's green and red and blue coming together, and that's compatible with my rule, because at that crossing, all three are different. So we see that this rule is compatible with the first Reidemeister move, the second Reidemeister move, and in fact, we could check more cases to see that it's compatible with the third one. So this property of being colorable with this rule stays the same as I do all three of the Reidemeister moves. With me? And now I want to have a non-trivial coloring. By non-trivial coloring, I mean with more than one color. So the question I'm going to ask myself is, which knots have a Cree coloring with this rule with more than one color? Of course, every knot has the silly color, the trivial coloring, where I color it all one color. So that's not of interest, but I want to do it with more than one color. Okay? And now you'll notice that this one, the unknot, I can only color it with one color because there were no crossings. So this does not have a non-trivial coloring. This has only a silly coloring, and as I move it around, that's all I'm going to keep getting is that silly coloring, and I'm not going to be able to color it with different colors. No matter how I move it, I will not be able to color it non-trivially subject to this rule. Let's look at the trefoil and see, is the trefoil colorable? Well, okay, so for example, this strand over here is going to be red. Then there's going to be another strand which is going to be blue, let's say this one. And then there's going to be a strand that's going to be green, let's say this one. And now, lo and behold, you notice that at each of the crossings, we have all three colors. So this trefoil knot, haha, great success, is in fact three-colorable. This is an example of a three-colorable knot. And this one is not three-colorable. And the last one we're going to consider today is the figure-8 knot. Suppose that this strand was red, and then this strand, let's say, was green, let's say. Well, if this strand is red and this one is green, then this one, because it's the third one where they meet here, would have to be blue. So this one would be blue over here. Well, if this one is blue and this one is red, then this one over here also has to be green, because these three are meeting at this point, and that was our coloring rule, that they either have to be all three different or the same. But if this one is green and this one is green, then these two greens meet at this point, so the third one would have to be the same color. Remember, all three different or all three the same, so we'd have to have green here, but that contradicts that this guy was red. So we see that this one is not three-colorable. By this simple technique of studying three-colorability, we have proved that the trefoil and the figure-8 knot are not the same because one of them is three colorable, one of them is not three colorable. What we haven't succeeded at proving is we haven't yet proved that the figure 8 knot doesn't unknot, because all we know about the figure 8 knot is that it's not three colorable, and that happened also to be true about the trivial knot. So we haven't yet proved that these two guys are different. We've proven that they're all different from the trefoil, but we haven't yet succeeded at showing. But I could generalize this trick in a slightly more elaborate way for, say, 5 colors. And if I use 5 colors, this one would turn out to be not 5 colorable, and this one would turn out it is 5 colorable. And so the upshot would be that these two are in fact different. So by doing 3 colorability and adding on a further level of study to this, the 5 colorability, I would indeed have succeeded at proving that all 3 of these are different knots. In particular, there's no way to unknot the trefoil or the figure 8 knot without cutting it, and also there's no way to move, as we saw already, the trefoil into the figure 8. They can't get from one to the other just by continuous motions. Quite good for elementary just coloring around, don't you think?
Just because this one is 3 colorable and that one's, I mean, that just seems, and that one's not 3 colorable.
Because the point is that after I fill in the steps that I skipped over, right, or which I took an example of but didn't do the others for, that the point is that if a knot is 3 colorable, as I do these Reidemeister moves and move it around and change the number of crossings, the property of 3 colorability is maintained all the way through. For example, when I did the pigtail and I put in a pigtail, it was compatible. In fact, I adapted the rules so as to achieve this property and modified my original guess. And so if this is 3 colorable, as I move it around continuously without cutting it, though I change the number of crossings and may make it like the kitties thing, fantastically more complicated looking before I try to simplify it, nevertheless, at the very end, 3 colorability, if it was 3 colorable at the beginning, it will be 3 colorable at the end. If it was not 3 colorable at the beginning, it will not be 3 colorable at the end. And so the fact that one is 3 colorable and the other is not 3 colorable with the given projection means that there's no way to move this to that. And you can understand colorability better by developing the theory of polynomial invariants of knots. Specifically, there's an old polynomial invariant that goes back about 100 years. The polynomial invariant for this knot turns out to be delta of x. The Alexander polynomial is x squared minus x plus 1.